Good morning. And for me, it would be, I think, 1 o'clock in the morning or something like that. My name is Gimzewski. It's a great pleasure and honor to give this talk at the Supercomputing Frontiers Europe 2020 conference, virtually in Warsaw. I would have loved to be in Warsaw. And I'd like to thank, of course, the organizers, Marek, for doing such a good job at this rather hard time. We have this COVID-19 everywhere, and it's becoming a major problem in Los Angeles. But without further ado, I'd like to give you my presentation. And just, okay. So the title of my talk is Emergent Atomic Switch Networks for Neuroarchitectonics. And neuroarchitectonics is a term to describe architectonics, which is the science of architecture sort of applied to neuronal systems, in which we are sort of being inspired by the human brain. And if we look at the human brain, there are certain features that differ in terms of the operation of human brains. Firstly, we know brains are, you could say, analog, whereas computers are dominantly digital devices. And memory differs, you know. Our short-term and our long-term content addressable memory is not really like RAM. And it's, of course, the brain is massively parallel, whereas computers are working typically on the von Neumann architecture, sending information to and fro from processor to memory. Also in the brain, we don't have a distinction between, of course, hardware and software. And synapses, and we will be developing synaptic devices, and I'll show you some of the results, are much more complex in a way than logic gates. And the other thing is, of course, the brain is a self-organizing system. And what you can see in the bottom here is a couple of things that illustrate the problems when we try to make brain-like computers. And that is, if we look at the machine complexity required in terms of gates and so on, power, size, and we plot that against environmental complexity. And by that I mean the number of combinations, combinatorics involved, then the von Neumann machine scales really poorly. This was taken from a DARPA project description, which was about physical intelligence. So we're looking for something that does not massively increase in complexity. Note this is a log-log scale. And for that, we have to think of a new type of approach. Now, pardon me. We were inspired in our work by a couple of things, and I'll describe them in detail. The first is the structure of the neuropill. It looks like some tangled spaghetti mesh, densely connected. And in the neocortex, 60% of synapses occupy the brain by volume. The other thing is that when we look at system-wide activity, and this is functional MRI data of the brain here from Dante Scialvo, and you see this strange kind of behavior where information is distributed through the brain, or activity, oxygen levels, what have you. It follows a type of power law, which I'll explain in more detail. And the work on the right here is by Dietmar Plans, and it shows on a log-log plot in terms of activity and so on, and the size of the activity, that there is also a kind of linear relationship in a log-log plot that is typical of, but not necessarily only, self-organized critical behavior. Now, it's been argued for a while about this system-wide activity, but I think it's generally accepted that self-organized criticality does play an important part in brain function. And two people that really inspired me in this work were Dante, shown here. We're having lunch in Gdansk, very nice. And the late Walter Freeman, who spent his life trying to understand the brain in terms of, I would say, a kind of neural percolation model. Now, if we think of criticality in computing, we can think of Bach's work, for instance, called the sandpile model. It's a rather approximate model, but criticality suggests itself as something that's important for information processing, particularly of unstructured data sets. And it provides us a way to sense the global state of the system. And I'll give you an illustration through an Ising model of magnetic material. And we believe that it's important in most networks, human networks, swarm intelligence, and so on. And our idea is to try to generate a system that can operate in such a manner. So let's just think of spin, magnetic spin. And we have three situations here. We have three temperatures: low temperature, we have a situation which is near the second order phase transition, critical point. And then we have a situation where it would be the equivalent of, say, a higher temperature. And you see here, we don't have much correlation at high T. They fluctuate. It's very poor. And at low temperatures, in this case, the spin orientations don't fluctuate much. Whereas at the critical temperature, spin orientations, they fluctuate and are correlated. So if we look at T critical here, you can see how the correlation extends over a much wider distance than at both the low and high point. And this is what we would like to generate in our device. So we're replacing temperature in a way by energy flowing through a network. And I'll show you experimental data on this. So we would calve and expect this power law behavior. And you can see here near the critical point here between order and disorder, we can think more of a band of self-organized criticality that we would like to reach, and which it should reach by itself. Now, in terms of the dynamics, this is an illustration by Dante again, and it goes from a very simple system, linear systems, to nonlinear systems, and systems with a few degrees of freedom to many. So a simple system is predictable, is a pendulum, for instance, a single pendulum. But when we take many pendulums, these pendulums can exhibit a very interesting dynamical behavior. Likewise, if you take one ant and then you go into an ant colony, you will see a much more complex system in which some type of self-organized critical phenomena and pattern formation are formed. And probably way up in the high scale, non-linearity and degrees of freedom is actually the human brain. There are, of course, power laws not only in the brain, but in nature. And it's thought or conjectured by some people that we developed self-organized critical phenomena in our brain because a lot of the things in nature also exhibit these these system-wide spatio-temporal correlations. So here is our power law plots for a variety of activity. Brain activity I mentioned, neuronal activity I mentioned, but even things like solar flares, forest fires, earthquakes, extinction, right up to wars give this power law. And perhaps if we look at the COVID-19 and the way it's spreading throughout the world, it may also have some type of power law, which implies avalanche-like behaviors. So our research was stimulated by some need for an alternative computation hardware. Now I mentioned about conventional computers, fast, reliable, ordered, clearly defined inputs and so on. They're very good at some tasks. The problems with them are things like heat, von Neumann bottleneck between processor and memory, the speed of light. It's like hundreds of kilometers of wiring in an integrated circuit. As the devices get small, quantum mechanical tunneling through insulating layers. Size, as it's reduced, we have a problem with the heterogeneity and the doping of the system, and even just creating and destroying information involves some form of entropy in the form of KT log 2. And of course, finally, a big element is the economics of continually producing more complicated and smaller devices in terms of the fab cost. Now, today, when we think of supercomputers and so on, I have here the top. This is a variety of them. The top is the Chinese one. I believe it's still the most powerful. It's using 17.6 megawatts of power. And in no way really is it coming close to a human brain. And I think this is a little bit of a joke, but if we think of 10 ways AI could fight, for instance, climate change, this is a list here. Computer vision, time series analysis, unsupervised learning, and so on. You see for transportation, electrical, and so on. It's all been proposed to be a great way to fight climate change. But in actual fact, training an AI model can cause the equivalent emission of as much carbon as 5 cars in their lifetime. And here we have a US car, including fuel, one average lifetime. Here is the CO2 in pounds divided by 2 approximately for kilograms that are consumed or generated. And if you take some deep learning algorithm, you can see it's much, much more. So this is one big issue we have to be concerned with. Also, data centers, as you know, the demand is increasingly large, and a data center can use as much electricity as 25,000 homes. So at the rate the cloud's growing, it could produce as much CO2 as the US cars produce in one whole year. People are aware of that. This is from Wired magazine and is mentioning a couple of points that are quite interesting. If you look at how the development of these algorithms and deep learning and so on goes, you're getting to a point where the cost is becoming absolutely ridiculous. It's kind of exponential growth in cost. And so people are reaching the limit of scaling, but you know, there's room for optimization. However, it is still a major problem as we try to deal with more and more complex phenomena computationally and unstructured data. So I mentioned these in summary, the differences between the brain, networks, emergence, criticality, and computing. People are trying different things. people are actually trying to read people's brains using algorithms. And I think this is a piece of work from a Russian group in which it's rather interesting, but between real and reconstructed data from EEG signals, there has been some spooky advances. Our approach to trying to deal with complex problems, things like chaotic time series data and the likes, is to use reservoir computing. And I do know that in the maybe computing, supercomputing groups, reservoir computing just in a digital system, maybe not as attractive as the types of algorithms that are used at the moment. But it is very interesting to me when we have a type of network, which is in this case, in our case, analog network, for solving problems. The idea compared with a regular neural network is that we have no adjustment of the weights in the network. Although the network can be dynamic and adjust itself, but rather we just train the weights at the output layer. So we adjust those weights essentially by linear regression. But this is a kind of sketch of something by the McKinney-Moeller Institute, and I thought sort of describes that you have inputs, then we have some method here to adjust the output weights to the output layer, where we use linear regression. And these are some of the key parts about the device and the concept of using this reservoir computation or echo state property or whatever you would like to call it. But the interesting thing is that we would have in our device not permanent memory that we address, but rather fading memories. And these can be in the form of short-term fading memories or long-term fading memories. Our device is based on a thing called the atom switch. And way back 30 years ago, well, it's even more than 30 years ago now, we showed that with a scanning tunneling microscope, that's a sharp tip approaching a surface, conducting surface, in this case silver, that as we approach very closely, there comes a point where the atom jumps to contact. So this is basically a picture of the conductance versus distance in angstroms, which is 0.1 nanometer. And this contact resistance here equals what is known as the single atomic contact conductance or quantum conductance, has the units of 2e²/h. So this was an atom switch. But some years later, Masa Eono, who is in Scuba at the Materials Nanoarchitectonics Center, came up with the idea here of actually writing with atoms, in which he used the electro-ionic migration inside the device to deposit silver atoms from a silver sulfide matrix. So that was the first experiment. But later he was able to make devices here. And what you can see is the quantized conduction in units here, 2e²/h, versus different types of contact. And you can see the conductance is beautifully quantized back and forward in that experiment. And that led to try to build devices. And at the moment, NEC have produced actually not a neuroarchitectonic device, but a switching device which uses less energy and is more efficient than, for instance, FPGAs. And it's even been actually flown into space and tested on robotics, because in both of these situations, radiation or electrical noise is a major problem in space and also in robotics. So using silver sulfide and making atomic switches, we noticed some very interesting properties. Firstly, if we look at the conductance change as we pulse voltage through the device, this is also with an STM at the moment, you can see if we put in slow pulses, we get quantized conduction. But then when we take away the pulse, it disappears. Although as you repeat this, there's some fading component building up. Now, if we actually make the frequency of the pulses much higher, then what happens is after a few initial pulses, it can then make a transition into a more permanent state. And this behavior here, depending on the frequency of excitation, very much resembles a model, psychological model called the Atkinson-Schriffen multi-store model, in which we have sensory memory going into short-term memory, then forgetting. But if it's repeated, like a piano lesson, for instance, every day, it can be shifted into long-term memory. And so we published that in 2011 as an example of a kind of synaptic device. And what you see on the left here is where we're putting in information, okay, in the form of 2 infrequently. You can see the fading memory of the conductance. And if we then change from a 2 to a 1, you can see that the 1 persists longer because it's been stored faster. And it's moving into the long-term memorization. So this is one element. Now, that's just one device, or 4 or 5 devices, let us say. The next step we took was to be actually inspired by the neuropill structure and combine 2 things. Firstly, normal type of fabrication of multi-electrodes in the central region, and the growth of wiring networks where each wire here made of silver is coated with silver sulfide that exhibits that interesting neuromorphic type of behavior. And when we generate these structures of silver sulfide and wires overlap, we have very complex networks where we estimate a synaptic interconnection density of about 10 to the 9 per square centimeter. And we can read up to 128 channels. These electrodes are underneath here. You can't see them in this particular drawing. So for a chemistry lesson, what we're actually doing is a type of electrochemistry which is, involves no electrodes, electrolysis deposition. And when we have the concentrations right, we can get a kind of diffusion limited aggregation growth. So let's say we take copper and treat it with silver sulfide, silver nitrate, then this causes a displacement reaction to form silver sulfide and copper ions. And then after that, we can react the system with just gaseous sulfur to form a thin silver sulfide layer. Now, when the pieces of copper, these are copper, small copper posts we use, are large. What we have is the formation of more like fractal or dendritic structures. If we decrease the size of the copper seed, the way we pattern it, then it goes from this, makes a transition into the formation of nanowires, which we found were more suitable than these dendritic or rhizomic like structures. So through size, we can change the network characteristics. And in terms of network fabrication, this is some of the steps. I won't go into the details, but what you can see here is different magnifications. And finally here, where we have these electrodes, we deposit through this DLA process a dense network of these nanowires, which are later treated with sulfur. And then it goes into a chip holder, and then we use typically LabVIEW and NEC instruments. And we don't multiplex. We read all of these inputs and outputs simultaneously. Perhaps in the future we could make it simpler by multiplexing, but at the moment we don't. So this is one of our students, former students. He now works with LabVIEW for the company, and you can see our experimental setup here, as well as the measurement interface here. So the first thing with these devices, which are memristor-like devices, is to generate a high conductance on state. And if you look at the bias voltage here being applied, you can see how the conductance increases. And this strengthens the network connection. But it can be kept quite stable. And this is the classic type of memristor curve. So as we increase the voltage of the switch on, as we decrease the voltage below a threshold level, it switches off. And this is the conductance of the entire network. But it very much resembles also a single memristor device. So our first observations of critical phenomena that we observed were firstly in passing just a 4-electrode system, in passing a current through this device, small current. We studied the network activity by using a very sensitive infrared camera, and we showed that the activity is distributed. There's still some electrical activity also in the sides of this device, obviously, but it's not a single filamentary pathway. Single filamentary pathways can exist in some devices, like in a more recent paper, we observed that in a different system. And if we look at the power spectral density here as a function of frequency, this is a log-log plot. For the for a system where we don't have sulfur sulfide, we get this type of behavior. But when we have the silver sulfide present, you can see that we get beautiful linear PSD frequency plot log, this typical power law behavior. And later we have simulated that in computers. That's a very simple simulation, but you can see here for isolated devices, this resembles a little bit our characteristics observed on the unsulfurized network. Whereas if we look at this a network of these memristor devices in terms of our theory, it also shows this linear plot in the log of the PSD versus log of frequency. There are some fairly recent models. These are our UCLA team results, also in terms of the IV characteristics here. And Deventra, he has also considered how electrical currents and avalanches flow through networks, similar to ours, but theoretically. And what you can see here is also this power law type behavior. And he has a model that involves electron tunneling and also sort of ballistic electron transport through the system. Now, in terms of data, if you look at the slope of the PSD, which actually is also seen where the slope of the PSD does change in, for instance, humans, whether they're sleeping or active and so on. What you can see here is, again, a log-log plot, log of the frequency versus the log of the amplitude in this case. And you can see how the PSD slope changes over time. And typically there are some characteristics when we use different currents and different voltages and so on, we can actually change the slope. And that may be something that's very important to adjust the network for certain computational tasks. Also, if we look at the voltage fluctuations in the device, this is interpolated a lot from the data in the networks, voltage fluctuations from correlated switching. You can see there's an interesting, there's an interesting resemblance between that and MRI data of the brain, neuronal activity. So this next part of the talk concerns the current neural networks we have. And there are some differences in the sense that we have a dynamical system, the memory of the input signal, and by adjusting parameters in terms of energy flow, we can operate these devices if we want at the critical point, the edge of chaos, which is said to have the highest computational capabilities for the RC device. Here are some examples of what we've been doing, and I'll show you some of these. One is a waveform generation, that is to take some input signal, and we have a target output signal, and train the output layer of the device to form these output signals. Second one is the T-Mage, which is a memorization task in which you imagine a rat is moving along here and he's given some cue to move left or right, some action, and then he has some reward and so on. And so the time between the action here, the pulse, so the trigger, and the action, which is take a left or a right, is a test of how long the memorization lasts. And the third one is chaotic time series prediction, in which we have data sets, say, in this case, traffic at LAX. For the moment, the traffic at LAX is probably down here, actually. And we also have performed that, as well as things I won't talk about, like NARMA, and so on. Okay, in terms of performance, this is our data, and I'm happy to say that in Japan, there are now several groups working with these devices, and they can obtain even nicer data than us, but it shows that, for instance, we input sine wave, we can output a cosine wave with a 90% efficiency, a triangle with 90% efficiency, and a sawtooth with 89.8% efficiency after a short amount of training of the output layer. We also find that its ability to make these target waveforms depends on the actual amount of energy we put through it. And we attribute that to basically higher harmonic generation. For instance, if you want to make a square wave, which is very hard, very difficult in a way, you have to have a whole range of frequencies. Whereas if you take a sine wave, obviously it's they're lower harmonics. And if we look at the situation here, this is conductance and overtones. So you can see the atomic switch has a high number of these harmonics, which is very useful in waveform generation. This is a simulation also that we have performed. So as you increase the voltage, you can see that the harmonics, like the second, the third, the fourth, change with bias voltage. In this case, previous work has actually predicted these enhanced overtones in this paper here. Okay, for the T-maze, let's see what we do. How do we simulate a T-maze? Well, basically we have a left input bias, a right input bias. We have an input signal, and we have a ground output signal. Very simple. Okay, so this would tell it to go right. This would tell it to go left, or vice versa. And so we start by applying a pulse to both to initialize the system. This is the trigger signal for it to move, say, to the right, the left, sorry. And then after some time, we pulse it again, and then we look at the voltage readouts and see if we can correlate those readouts with the prompt signal here to go in one direction or another. This is some of the data, and this is basically the target and the response. And in these initial experiments, we found we can be about 94% correct. So the experimental implementation of this thing is in real time. It's not computing and hanging around. Another thing we've been working on is to look at chaotic time series data. And this is an example. For instance, if we could take stock price, which again is also crashed. But if we take the stock price over a period of time, train the network, can we then predict the outcome when we don't know what the future is? Difficult. So we have done some chaotic time series traffic forecast results using our device. And in this case, we're only given a certain amount of data. We don't know what the rest of the data is. We train the network, and then we try to predict future behavior. And according to people that worked on this particular problem, we have a comparable performance to the top 25 percentile in the neural forecasting competition. So, we have a long way to go, but I'm just showing you where we have some strengths and where we can move forward. So what are the current directions? The current directions in our work are we don't need programming as in CMOS, but we would like the system to be compatible with CMOS. One of the issues is the encoding schemes of the input data. There are so many ways that we can encode data, spike timing, all sorts of things. But what is the best one for the network? And that's something we have to really establish. Also, in terms of the material systems, we have now moved to other selenium, iodide systems, and so on for generating networks that have different characteristics in terms of the memories, memorization in terms of the operational voltages. And of course, we have network topology, which is also a parameter to investigate. These are some things we thought about, particularly the ability to generate very tiny batteries, equivalently electroionic batteries that would also self-power the system. And we have fabricated those. So this is the way we see ASN. It's not going to replace CMOS, but it's going to have a capability to do things which make the CMOS process, the CMOS electronics here, remain fairly simple and scalable, we hope. So we call that a hybrid 3D architecture. And moving into 3D is another thing we have in mind. So from taking Walter Freeman and Cosma's work, what you can see is this is the structure of the neuropil. His model, Cosma's model, was this percolation, neuropercolation, sort of random cellular autonoma model. And this is CASA chip, because originally we called it CASA, we call it Atomic Switch Network now, but it's essentially the same thing. And these three things are very, have some similarities. So the function and dynamics, in terms of both the percolation model and our device, like the formation and metastable patterns due to phase transitions in the sulfur sulfide sulfur networks, and the ability to generate a situation where we can be critical or supercritical or subcritical, essentially, in the network behavior. So recently we have published another paper using completely different material systems, and we find these emerging dynamics also exist. And this is for the case of PVP, is polymer-coated nanowires. And when these nanowires come together, these are pictures of the nanowires network. They have this thin PVP layer that can be seen from this electron transmission electron micrograph. And when they contact and we apply a voltage, we can get then a kind of diffusion of the silver through the polymer, generating a conducting pathway. Okay, well, I'll finish off my talk by just mentioning a couple other things that might be fun. I did mention how do we encode the data, and some methods are by amplitude, by frequency, or spike numbers, or pulse width, and we have explored all of these, but we are far away to find what is the optimum encoding method. In fact, the encoding part is a bit like maybe how you would deal with digital data to some extent, except this is, of course, an analog, fully connected network where the computation is being done within the network, not a part of the network. Could this be used to, for instance, connect to the human brain? I mentioned at the beginning those interesting examples of people being able to read or look at images of what people are thinking or seeing by using these electrodes, EEGs. And we have been exploring this with particularly people in Switzerland, which is making, a device. This is one that's used actually for neurons or cardiomyocytes. We have one. We have synthetic neurons, natural neurons, and how do we connect those up? And in terms of measurements, it would be interesting to use these machine learning algorithms and so on to understand how a biological neuron network interacts with such an artificial network. These are some of the cell models that we have considered for this work, and also how we can use machine learning in relationship to neural networks. Okay, so let me finish my talk by telling you some other work. I am the director, scientific director of the Art Science Center, and this is work by Victoria Vesna, who is an artist in the Art Science Center. She's the director. And working together with neuroscientists, what they did was generate a very interesting system where these two people have electrodes on their head, and this data goes into a computer and generates sound, and it generates colors. So each person has their own sound and their own colors. And what they found, which is fascinating, is that certain people who meditate, actually, they're better at it than others. They can actually somehow synchronize their brain waves in terms of alpha and beta and so on by sounds that are created by them, essentially, and by the colors that they also create. So these colors can be completely different. This is a case of synchronization. Other interesting work that's going on is connecting up with physics, essentially, with, in this case, art. And instead of talking about artificial intelligence, we know that Takeshi Ikegami, who's very famous in this type of work in Tokyo, and Charles Taylor, who's an evolutionary biologist, have generated a piece in which the public can actually get a feeling for how networks exist. And this was funded by the NSF, also in terms of acoustic communication networks of birds. And this is the piece that was done in Tsukuba, in the University of Tsukuba. This is the biggest VR space in the world. And it uses a kind of algorithms, very interesting algorithms that generate this type of flocking behavior. And this is an extremely complex simulation done by Takeshi. So to finish off, I'd like to acknowledge the people involved in this along the way, in particular Adam Stieg, who has initially worked with me on the project, and we still work together. These are various students who passed through our group. Also Masakusa Iono in the National Institute of Material Science in Tsukuba, along with these other people who have all worked, and everybody here has produced papers on this subject if you go online. And originally, I want to thank also people at HRL in Malibu, Walter Freeman, the late Walter Freeman, and Robert Kozma, who contributed greatly to some of the ideas. And a lot of this work was achieved through the DARPA program, Physical Intelligence, that actually brought together people from different areas. Some of them were historians, some of them were psychiatrists, psychologists, physicists, all sorts of people, to try to understand what physical intelligence is. And I think we still are a long way away from it. Finally, in 2002, I was in a conference in Sardinia, a very small conference, and this is Heine Rohrer, the Nobel Prize winner. He's now passed away for scanning tunneling microscope in '86. This is me when I had hair, and Sir Mark Welland here. We all got together to try to brainstorm, and this is what we came up with: challenge and understand and communicate the brain. And I think it's really interesting that, like 20 years later or something like that, we actually are starting to work on those problems, and people are in various areas maybe starting to glimpse at how the brain works. And once we can do that, I think we will make new types of devices, like along these lines of networks or analog networks that will be integrated, hopefully one day, into cell phones. Anyway, thank you once again. I'm really sorry that I couldn't come to Warsaw. My father was a Polish refugee from the war. And I have been back to Poland many times, and I also sort of consider myself to have Polish blood. Anyway, thank you all.